briefly introduce you and the subject.
Sure.
Okay, hi all. Uh, so today we have Dawood here, and I'm very happy to invite. A couple of people are asking permission to join. Let me just permit them. Okay, so Dawood is going to give the Nobel talk on physics today. And this is the second occasion he is giving a talk in CUSAT. Last year, he visited the department as a part of workshop on the emergent gravity paradigm. It is just that this time his visit is virtual. Now about Dawood's career, he did his PhD at IUCAA under the guidance of Professor Thanu Padmanabhan. After his PhD, he worked as a postdoctoral researcher at the University of
Charles, I think your voice is breaking.
Oh, okay.
Problem maybe with the headphone.
Can you hear me? Am I audible?
There is a breaking in the voice.
Just a second. How about now? Is it fine?
There is some disturbance. I think you can talk without the headphone.
Okay, fine. Hello. Is it better now?
Okay.
Okay, fine. Yeah, after PhD, Dawood did a postdoctoral research at the University of New Brunswick.
Is it audible to others, or I have the problem?
Yeah, a couple of people commented that it's audible.
Yeah,
okay.
It's audible to me.
It's okay.
Okay. And after his postdoc, he joined IIT as an assistant professor, and he has been there ever since. Dawood's main area of research is in gravitation and cosmology, where he investigates aspects of classical and quantum gravity. Today, he will talk about a topic which is probably closely related to his own research. That is space-time singularities in black holes and cosmology. As we know, this year, a Nobel Prize has been awarded to people who contributed to understanding black holes, both theoretically and observationally. And if you remember, this is the second consecutive year this coveted prize has been awarded to the field of astronomy. Last year, it was awarded to cosmology and planetary science. And in particular, last year, a pioneer in modern cosmology, Professor Jim Peebles, was awarded the prize. This year, there is another pioneer who is in black hole physics, is awarded the prize, and who is none other than Professor Roger Penrose. In this talk, Dawood will focus on the important contributions of Professor Penrose. With regard to everybody, I welcome Dawood to deliver the talk. So all others, rest of the people, can they mute the microphone? Okay, so Dawood, please.
Yeah. Thanks, Charles. Thanks for the nice introduction. It's good to be speaking again to audience in CUSAT. Just wanted to make sure if my voice is properly audible. It's not breaking or anything.
Yes, good.
Thanks a lot. So, as Charles already mentioned, the topic of my talk would be space-time singularities in the context of black holes and in cosmology. And the discussion in the talk would essentially be in the context of this year's Nobel Prize, which was awarded, as Charles already mentioned, to a theoretical result in black hole physics, as well as observational aspects of detection, one of the first detections of a supermassive compact object at the center of our own galaxy. This talk will mostly focus on the mathematical physics part of this year's Nobel Prize, essentially the work of Professor Roger Penrose. And it's also right at the beginning, I must highlight that this is an extremely unusual choice for Nobel Prize, because this is probably the first time when it is being awarded to a result popping out of pure mathematical physics. I will explain the kind of ideas that went into the result for which Penrose has been awarded the Nobel Prize. But it's probably worth emphasizing that Einstein himself never received his Nobel Prize for formulating, for the mathematical formulation of general relativity. There have been many prizes given for observational aspects of GR, but for the formulation itself, there have been no prize till the current year's prize to Penrose for some really remarkable mathematical results in relativity. Okay, so what I will do, and that's the plan of this talk, I will start with a very quick introduction to general relativity for those who are completely new to the field. This will be a very very quick and a broad overview of what gravitational physics in the language of Einstein, in the language of differential geometry, essentially says, how it is different from Newtonian gravity. And then I will immediately jump on to the discussion of some of the most exotic solutions of Einstein's gravitational field equations. These are the black hole solutions. And these are the solutions which also contain within themselves hints of singularities. And these singularities, although you might initially think are very similar to singularities you would naively encounter when you are solving Maxwell's equations, for example. You know that the Coulomb's field of a charge is 1 by r square. Coulomb potential of a charge is 1 by r. So all of these things diverge when r equal to 0. So at the first sight, you might say that there's no big deal, that just like Maxwell's equations have singular solutions, Einstein's equations for gravity might also have singular solutions. But I'll try to convince you why the singularities appearing in Einstein's theory is much more tricky, much more subtle concept, because you're talking about not some field living on a fixed space-time. You're not talking about things like electric field or magnetic field living on a pre-given space-time. You are talking about fractures and tears in the space-time itself. Okay, so I will just try to introduce this idea and also give you a flavor of the kind of mathematical arguments which won Penrose this year's Nobel Prize. Okay, so let me start with the GR part, and the framework for gravity, which is described by general relativity, starts with one of the great insights from Einstein. And the insight is simply that gravitation can be understood in terms of geometry of space and time. So what Einstein did was displace gravity as one of the forces, which was the Newtonian line of thought for centuries, and replaced it by a new idea that it's not a force, rather it's a manifestation of space-time geometry. And that's what happens, for example, to a simple system of Earth and Moon. So what happens is that Earth and Moon distort the geometry in their neighborhood, and they are both moving, as well as every other object around them are moving in this distorted geometry. And that is what we feel as gravity. Okay, so before I go to general relativity, I will only discuss the key points from general relativity which are required for singularity theorems. And as I hope to convince you all, very few details of the field equations of general relativity are needed to discuss singularity theorems. This is essentially why the results of Penrose were remarkable. They have a very broad application, and even if tomorrow somebody comes and changes the field equations of general relativity, a large part of singularity theorems will still hold. Okay, so I will only give you a brief overview of the part of GR which are absolutely crucial to understand certain mathematical terms in the formulation of singularity theorems. Okay, let me start, before going to GR, let me start by refreshing your knowledge of a little bit of what special relativity is all about. And these kind of structures is what play a key role in Penrose's formulation of space-time singularities and the singularity theorems. So what you see on the left-hand side is the version of space and time as Newton would have described it, as we have been using in our classical dynamics course all along. So basically what we do is we imagine three-dimensional space. Here it is depicted as slices of two-dimensional space. And a progression of these two-dimensional space in time is what is described by Newton's laws. You can take Newton's laws of motion or Newton's laws of gravity or whatever it is. Mechanics is described by the history of space, which is three-dimensional, as it evolves in time. And as I'm assuming all of you would have studied in your basic introduction to special relativity, Einstein's special relativity changes, postulates of special relativity drastically changes this picture. You no longer have a stack of spaces, stack of three-dimensional space moving forward in time. Instead, what you have is your own location in space-time marked by what I've written as U here, okay? And you have what is called as a future light cone. So from your location, you send out light rays in all possible directions. And the domain which is formed by these light rays is what is the shaded orange region in that figure. You can similarly construct what is called as a past light cone, which is the past piece of the cone shaded in orange there. And these regions are regions which you can affect or which you can communicate with by sending light rays. Similarly, in the past, the regions which are shaded there are the regions which can communicate with you at the present time. So rest all of this figure is irrelevant as far as you are concerned, because you cannot exchange signals at the present time from much of this region. So much of space-time outside the light cone is what is not technically called as causally connected with you. And this causal connection, these relations between different points in space-time obtained by your ability to communicate with a region, or the ability of a region to communicate with you using light rays, is what is a key ingredient in the singularity theorems which Penrose formulated. And as we go along, we will see the significance of this. So that is why I thought it is good to refresh your memory. So we will use light cones a lot when we discuss black holes as well as singularity theorem. So keep that in mind. Okay? So that's all something that you could have already understood from special relativity. You can now go ahead and also briefly realize what happens in general relativity. So the picture I just showed you is valid as far as there is no gravity. But if you want to actually construct a relativistic framework for gravity, that presents a remarkable new challenge. And the challenge essentially comes from an observation which has been known to us for centuries. The observation is that an apple and a feather, as shown in that slide, will fall at exactly the same rate near the surface of the Earth. They will fall with the same acceleration, 9.8 meters per second. So, of course, this has been known since the time of Galileo. That's a famous experiment of Galileo. But the important question is why is it true? Why does that happen? So I have written two elementary equations of high school mechanics there. First is the Newton's law of motion, that force should be equal to mass times acceleration. And this is the mass which correctly should be called as inertial mass of a particle. That's the object which gives particles their inertia. The second equation is a formula for a specific force, that's the force of gravity, which near the surface of the Earth is proportional to g, acceleration due to gravity. And the parameter m which appears in the second equation is what I've called as m gravity. Okay, so gravitational mass in principle can be different from inertial mass. And it's an experimentally verified fact that for all the objects in nature, gravitational mass and inertial mass are proportional to each other with the same proportionality constant. And this is the reason why acceleration produced by gravity on various objects are all the same, because the ratio in that equation is the same. And this is a very special, this is something very special to gravity because it doesn't work, for example, for electromagnetism. For an electric field, the acceleration is proportional to q by m inertial, as I've shown in this slide. And that is the reason why different particles will move, different charges will move with this different acceleration in an electric field, but different masses will move with the same acceleration in a gravitational field. And this really, although it took 400 years to recognize this very, very basic, the importance of the very basic question, the implications are very interesting. What it says is that if everything falls with the same acceleration in gravitational field, then maybe gravity is not something which manifests as a force, but rather it is something which has to do with the background geometry itself. Because if objects are moving in the same geometry, then you don't expect them to move with different accelerations. They'll follow a fixed trajectory, and hence you will find their acceleration to be similar. Okay, so that is what happens to space and time of Newton finally in Einstein's general theory of relativity. I had indicated the connection in special relativity earlier, and this is the connection in GR. So instead of space and time like Newton or space and time like special relativity, if you have masses interacting gravitationally, then a good way of thinking about them, as Einstein taught us, is to imagine that these masses are distorting the geometry of space and time, and every motion is happening in this distorted geometry. That is what you interpret as a gravitational force in the language of Newton. And here is a simple example which illustrates it. The simplest example of a curved surface is a surface of a sphere. So you can just imagine two ants moving on that surface of a sphere. If they are moving on the shortest possible curve, the curve of shortest possible distance on the sphere, which is a great circle, this is how their motion will look like. They are just following the straightest possible lines on the sphere. There's no force between them. But this is how it will appear to an external observer who cannot see the sphere. He or she will interpret this as an attraction between the two ants and will call it as a force existing between them. This force is given a very technical name, a name which all of you should be familiar with. It's called as a tidal force. And again, that is the second object which will play a very, very important role in the proof of singularity theorems. Okay, so the idea, the way I'm progressing here is that I am giving you very elementary concepts. And I hope by the end of the talk, you will realize that how these elementary concepts play a key role in formulation of some of the technically most interesting results in Penrose's work. Okay, so so far so good. That is what we have. The extra ingredient which Einstein used to finally arrive at a geometric formulation of gravity is what is called as the equivalence principle. And the idea essentially is, again, using the same fact that acceleration due to gravity is the same for all objects near the surface of the Earth. What you can argue, although I'm not going to follow up with this argument, but what you can quickly argue that this allows us to mimic the effects of gravity by simply going to an accelerated frame of reference. Intuitively, this is very easy to understand. If all objects are moving with the same acceleration near the surface of the Earth, for example, in a very small lab near the surface of the Earth, then you may just go to an accelerated frame of reference, and you know that when you write down, for example, Newton's equations in an accelerated frame of reference, there are pseudo forces which come, and these pseudo forces can mimic precisely the effects of presence of gravity. So in the picture on the screen, for example, on the left-hand side, you will interpret, if you have a lab and there is a ball on the roof of the lab, which you let go, it will fall down with an acceleration of 9.8 meter per second square. On the other hand, the right-hand side, if you are in outer space, no gravitational field, and you accelerate upwards, once again, the net effect would be the ball moving from the roof of the lab to the floor. Okay, so the net effect is exactly the same. The outcome of both these experiments are the same, and hence, locally, you can always replace gravity by going to an accelerated frame of reference. So this is the picture of gravity which general relativity presents to us. And like I have already said, one of the key ingredients which will also appear in singularity theorems, in the proof of singularity theorems, is the idea of tidal forces. And that is what I have indicated here. Okay, so this effect is very easy to understand, and it's the effect which causes tides on the surface of the Earth. So the idea is that if you are near a gravitating object, then the gravitational force at two different points of this object, for example, the gravitational force at the feet and the head would be different. It will be stronger at the feet, and this will have an effect of stretching the object in the vertical direction, the radial direction, so to say. It will also have the effect of squeezing in the perpendicular direction, and that you can easily work out by using just the laws of Newtonian gravity. You don't even need general relativity for this. Okay, there'll be a squeezing in the perpendicular direction and a stretching in the radial direction. And this is the same effect which causes, for example, tides in the oceans on Earth, the gravitational gradient, the gradient of gravitational force produced by sun and moon. Okay. And we will see that when the gravitating object is extremely strong, it's producing an extremely strong gravity. In particular, when you're looking at something like a black hole, the tidal forces are enormous. And that is really, tidal forces are already enormous for a small enough black hole. But near the singularity, these tidal forces, most of the time, become divergent. They are extremely large, tending to infinity. Okay, and this is what distinguishes a singularity from, or rather a black hole, from something like an Earth uh, of the same mass. A black hole of the same mass would be so compact that the tidal forces near the center of the black hole would be enormous. So let me go ahead and tell you something about Einstein equations. I am telling Einstein equation in words here because that is what will matter, but I'll also write down some equations later down the line. So eventually what Einstein's equations of general relativity tell us is that curvature of space-time is determined in terms of energy and momentum of matter. Okay, so for example, curvature produced by Earth in the space-time geometry around it will be determined by the mass of the Earth and maybe other matter content that forms the Earth. We'll come to that later. But that is essentially the content of Einstein's equation, and it's often quoted in the below words of Wheeler, that space-time tells matter how to move and matter tells space-time how to curve. Okay, so that is the key mantra of general relativity which Einstein taught us. What we will need is a form of Einstein equations which is much simpler than the form in which it is often discussed in textbook. So that is the form I'll indicate to you when we discuss singularity theorems. But this is just to give you an idea of what Einstein equations are all about. Okay. And here is a little bit of math because we might be using some of these quantities later on. So since we are talking about geometry of space-time, what we are really talking about is how to measure distances between space-time events, because you would have learned in your basic geometry as well that if somebody gives you a measure of distance between 2 points, any pair of 2 points in a given space, it completely determines the geometry of that space. If I tell you how to measure distance between any 2 points on the surface of a sphere, if you compile this information, it will tell you about the geometry of the sphere. If you do it on a flat sheet of paper, it will tell you about the geometry of the flat sheet of paper. Okay, and this distance is determined in terms of a matrix, a 4x4 matrix, which is called as the metric tensor. So that is one basic object in general relativity. And this metric tensor, after a complicated manipulation, you can take derivative, all those things of the metric tensor. It gives rise to a 4-index object. It's an object with a very large number of components. That is effectively what is called as the Riemann curvature tensor. And we will see that very often singularities in space-time, singularities at the center of black hole, or singularities at the beginning of a universe, are also accompanied by divergence appearing in the Riemann tensor. Okay, but once again, and there's an interesting history to this particular comment. Many people thought that divergences in curvature tensor are what should be taken as signals of space-time singularities. Because if curvature of space-time becomes infinite anywhere, that is a good reason to believe that there is some kind of a singularity in space-time. This is same as electric field of a point charge becoming infinite at r equal to 0, location of the charge. So you are tempted to say that the location of the charge itself represents the singularity of the electric field. But as I mentioned right in the beginning of the talk, this turns out to be a very tricky characterization of singularity and is not what was used by Penrose himself in his formulation of singularity theorems. Okay. So we'll come to these points as we go along. Yeah. So effectively, what I have said so far is a very, very broad overview of general relativity and how it describes gravity as a manifestation of geometry and curvature of space and time. Okay. And the first indication of what might be the implication of such a theory was in the study of formation and evolution of stars is effectively the field of stellar physics. Okay, so because this is a key problem in gravitational physics, right? What is the ultimate fate of a collapsing star? So till Einstein's general relativity, we know that in Newtonian theory, collapse is described by the Newton's laws, Newton's equations of gravity. Okay, so you have a star with some density and pressure. You can use the laws of Newtonian gravity, and you can describe how the radius of the star will change as it collapses under the force of its own gravity. Okay, it's a complicated computation, and I'll give you a flavor of that computation in a couple of slides. But one can do the calculation in Newtonian physics. But important question that one must ask when discussing collapse of a star is this collapse ever going to stop? Will it be halted by the by the matter content inside the star? There are fusion reactions taking place within the star. We all know that, and this fusion reaction produces pressure. There are other sources of pressure inside a star, and it might just happen that pressure will eventually win and gravitational collapse will eventually stop. Okay, so the question is whether this will happen always. We will see that the Einstein equations can be recast in a manner which says that under very realistic conditions on matter, pressure does not help you win, and eventually it is gravity which will win and the star will collapse completely. Okay, I'll give you the equations which are actually very simple in a moment. But let me also come to the final question in the formation and fate of stars. And that is, what does Einstein's theory actually say about the eventual outcome of gravitational collapse? So suppose you do agree that gravity eventually wins, pressure support inside the star does not continue forever. Eventually the star collapses under its own gravity and it keeps collapsing. Then a natural question is, what is the eventual outcome? Will the collapse ever stop? If it does not, what happens to all the matter that has collapsed? And that is where the concept of singularities will eventually come in, the final fate of the ultimate gravitational collapse once the pressure sources inside a star are no longer able to support the star. Okay. So while we are discussing black holes, it is probably worth mentioning that the idea of existence of a black hole itself is pretty old. As you can see from the years quoted here, it was actually formulated by Michel and Laplace in the 18th century, late 18th century. And the idea was simply that, if there is a star, there's a concept of escape velocity from the surface of a star. And if that can exceed the speed of, that can equal the speed of light, then even light will not be able to escape. So the idea is not completely strange by itself, but actually the argument given in terms of escape velocity turns out to be slightly conceptually incorrect. The more modern argument comes from a very precise computation, the first of its kind, which was done by Subramaniam Chandrasekhar, who actually proved by using the equations of statistical mechanics and gravity. He imagined a collapse of stars with certain matter content and asked what is the point at which gravity will eventually overcome the pressure produced by the constituents of the star. Okay. The conclusion he came to was that gravity will eventually overcome the pressure of electron degeneracy. Okay. So you go to the ultimate state of matter where there are degenerate electrons. Okay. You have all learned in statistical physics that there will be electron degeneracy pressure, essentially because of Pauli exclusion principle. And you can actually ask, when will this pressure be completely dominated by the gravitational inward force of attraction? And that is when the gravity will win and the star will continue to collapse. Okay. And the answer was that when the mass of the star is somewhat greater than 1.4 times the solar mass, this is going to happen. Okay. So I can summarize this whole discussion. There's a very interesting history behind this whole set of computations, including the history behind Chandrasekhar's discovery of his result. But the effective final results are indicated in this plot, very important plot, which indicates ultimate fate of a star. So the vertical axis here is mass of a star in units of mass of sun. The horizontal axis is circumference of the star in kilometers. And you see that if the mass of an object is very low, so you are much lower down in the vertical axis, Chandrasekhar's result actually applies. At some point, similar to the arrow which says death of sun, which is a sufficiently low mass star. So this, for example, will lead to whenever sun collapses eventually it's going to happen, and its radius decreases to a certain extent, it will come to a state, an equilibrium state, where the electron degeneracy pressure will just balance the gravitational attraction, and the sun will find itself in an equilibrium state and settle as a white dwarf. If you have a more massive star like Sirius, which is indicated towards the top of the figure, something else will happen. Okay, more likely, the fate of Sirius cannot be avoided just by appealing to electron degeneracy pressure. And that is what Chandrasekhar had found. So if the initial mass of the star is too large, then even electron degeneracy pressure cannot balance gravity. Star will continue to collapse. But you know that the story does not stop there, because electrons are not the only subatomic particles which the star is made of. At some point, you will have neutron degeneracy pressure. So the question is whether neutron degeneracy pressure is enough to stop the collapse of a star like Sirius, or whether even that becomes irrelevant at some point. Okay, so this is a cartoon picture. A more precise result is indicated in this particular figure, which I'm not going to discuss in too much of detail. I just want you to focus on arrows marked as death of Sirius and death of a star called as Procyon. And you see that one of them might just end up, if you follow the arrow, it might just end up on the barrier which is marked as neutron star graveyard. It's often called as the neutron star graveyard. So Procyon, a star like that, when it dies, eventual outcome might be a balance between neutron degeneracy pressure and gravity. But for a star much heavier than that, eventually even neutron degeneracy pressure may not be able to stop the collapse, and it will eventually collapse to form a black hole. So I think I have sufficiently convinced you guys that eventual fate of collapsing objects is that of formation of a black hole. And what I'm going to do next is assume that a star was sufficiently heavy, the mass was sufficiently high, so that neither the electron nor the neutron degeneracy pressure will be able to stop or halt the collapse of the star. And eventually it does form a black hole. So the story of singularity theorems actually will start by asking what happens next once a black hole has formed, what is at the center of the black hole, and what is the eventual fate of the collapsing star. Okay, so here are just a few facts about black holes, okay, which you might have read somewhere, but let me summarize it anyway. So black holes are characterized by a region which you call as an event horizon. This is a region, it's a boundary of the black hole region, and that is the surface. If you cross this surface, you will not be able to communicate with the outside world by light signals. Okay, light cannot cross this surface. And the radius of this event horizon is given by the formula in the next point, 2gm by c square. M here is the mass, the initial mass of the star which had collapsed. Okay, so if the black hole is non-rotating, that's the expression for event horizon of a black hole. But this formula you can use to actually, just for fun, compute event horizon of, for example, Earth and Sun. I have indicated it there. If you compute it by plugging in mass of the Earth, event horizon is about 5 centimeters, ridiculously small. For Sun, it will come out to be about 3 kilometers. Okay. What it tells us is that event horizon for these objects, or most objects we see around, are buried deep inside their actual radius. Actual radius of the Earth is much larger than this. Same for the Sun. And that is why it's highly unlikely that any of these guys will ever form a black hole with a collapse. Okay. The next point I want you to just remember is that space-time curvature at the horizon of the black hole. Remember the Riemann curvature tensor I had indicated? That is proportional to 1 over square of mass of the black hole at the location of the event horizon. And I already said this thing earlier. If a black hole is small enough, then the curvature will be sufficiently large at the horizon. So the tidal forces which are governed by curvature will be large. But usually for very large, very heavy, very massive black hole, curvature at the horizon is not too large, okay, because it is inversely proportional to square of mass, okay. And finally, I have already said this, but just to repeat, for an outside observer, event horizon is a boundary of the accessible universe. because anything that falls across the event horizon cannot communicate with the outside world. Okay? So before I directly jump finally to the discussion of singularities inside the black hole, since I'm not going to be talking about the observational aspects, I'll just flash this slide, which gives you some idea about how black holes are observationally detected. So this is a snapshot of a very, very compact region at the center of our galaxy. And there are several stars whose astronomical coordinates are plotted there. And you see, you keep a track of orbit of these stars, and eventually from the shape and the velocity of these stars, you can compute the mass of the central object. And this is how you detect actually that the mass of the central object, when compared to its size, satisfies precisely an equation like the one in the second line here. That is why there is a very good evidence that a compact object at the center of our galaxy is actually a black hole. Okay, this is the part I'm not going to talk much about. Okay, so let me now come to the question of singularities. What happens to the stuff which has actually crossed the event horizon and formed a black hole? Okay, and we are going to start from basics. Okay, so let me write down first the well-known laws of Newtonian gravity. That's the first equation on this slide. That equation just says the divergence of gravitational acceleration or gravitational field as a vector field is minus 4 pi g rho. This is your basic equation of Newtonian gravity you would all have learned. Okay, and the next equation is what I had promised you earlier. It's slight application of Einstein equation, but it's essentially an equation which is going to be more useful for us in discussing singularities. That's the reason I didn't even write Einstein's equations completely. Okay. So the second equation comes from general relativity, and it tells that divergence of gravitational field is given by an almost Newtonian looking like equation. First term is 4 pi minus 4 pi g times the mass density. But the key point is that there is an extra term here which comes from pressure. That term is 3p by c square, where c is the speed of light. So obviously this term did not exist in Newtonian theory because speed of light there is assumed to be infinite. Okay, it's a non-relativistic theory. So that's why you did not have a pressure term in standard Newtonian gravity. But this tells you that if you have a source of pressure inside a collapsing star, beyond a point, it's really not going to help. Because although outward pressure apparently seems like it is balancing the gravitational inward collapse, a positive pressure also contributes to gravity by the second equation that I have written here. Okay, it only adds to the mass density. Effectively, it acts like an additional mass density, and hence it will actually help in further gravitational collapse. Okay, and this is essentially the reason why beyond a point, nothing can halt collapse under gravity. Okay, because any kind of pressure will also produce a gravitational field, and this gravitational field will eventually lead to the ultimate collapse of an object. Okay, so that is the key feature of general relativity, which actually makes formation of singularities inevitable. Okay? The way we'll study singularities in the next few slides is we'll look at bunch of test particles whose trajectories I have drawn here.
Sir, I have a doubt about this pressure. So how come is it possible that pressure will actually reinforce actually will add up with the effects of gravity?
Yeah, that's just evident from the equation itself, right? Because rho
is
plus,
there any way to understand? Physically, is there any way to understand why pressure is like rather than like holding the gravity, it's like contributing?
No, I cannot give you a pictorial way of understanding this, but because it essentially comes from the fact that all kind of stresses, energy, momentum, everything gravitates in Einstein's theory. Okay, and pressure, or rather any kind of a stress in a material media, also acts as a source of gravity. So that is just how the theory is formulated, and that part is what is not true in Newtonian theory. Okay, I understand what you are trying to ask, but really there is no intuitive picture of.
Yeah, but then there is one more question. Then why at the earlier stage it was opposing the gravity? Like initially, why it was opposing?
Yeah, because those effects came from the full set of equations. Notice that here the equation I am giving is just for a divergence of the gravitational field. Okay, what it tells you effectively is if you have a bunch of particles like I have shown on the right hand side, whether they will come together or whether the trajectories will move apart from each other under the gravitational influence. So that is what this equation says. Okay, full computation should also include other quantities because this is just the gravitational interaction. The full computation will also include interaction coming from quantum effects, interaction coming from fusion, and all those kind of things. Okay, that is not incorporated in this equation. You have to combine both the analysis.
Okay. Thank you.
Okay, yeah. So continuing with what I was just telling him. So the way I want to do the further analysis is take a bunch of test particles like I've drawn here. Okay, and imagine that these test particles are moving in some gravitational field. Okay? Look for the relative acceleration of these test particles. That is, take the separation which I have indicated by xi I and compute the acceleration, that is the second time derivative of this separation vector. Okay, this is actually what is called as a deviation vector in GR, and you can compute its acceleration. Divergence of the deviation, divergence of that acceleration is what I have indicated here. Okay, so that basically tells you that if you have a bunch of test particles, whether they will accelerate towards each other or away from each other is going to be determined by the sign of rho plus 3p by c square. Most realistic matter will have that quantity as positive, which is why gravity is attractive, which is why a bunch of particles moving in a gravitational field will mostly tend to bunch together. Okay, if the external gravitational field is produced by realistic sources, then mostly the test particles will try to come together. Okay? So, and we know singularities already exist in solutions of general relativity. Okay, so since I'm not going to be discussing details of how these solutions come, let me just give you a flavor of what singularities look like in simplest solution. So if, for example, you have a black hole with some mass m and it's not charged and it's not rotating, then remember this metric or the formula for distance function I had indicated in the beginning of the talk, that for a black hole, simplest kind of black hole, this is called as a Schwarzschild black hole, is going to be given by this equation, where the function f of r is given by 1 minus 2gm by c square r. You can compute the curvature corresponding to this geometry by a complicated expression, and you can show that whenever r equal to 0, curvature diverges. Okay, so that is one example. So that this was the understanding of people already much earlier in the development of relativity, that there is some kind of singularity at r equal to 0. Same happens with the universe as well. Our entire universe is described by a similar geometry, which is much simple. Average universe is described by a very, very simple measure of distance between 2 points. And it's all governed by what is called as a scale factor. It measures what is the size of the universe at a time t, and it's denoted by a of t. The solution for a of t comes by solving Einstein's equations, but you can show that the curvature for all these kind of geometries also diverge when a of t goes to 0. Okay, and this is the point which we call as Big Bang. Okay, whenever the size of the universe goes to 0, curvature diverges and there is a singularity. So this is just to tell you that there are singularities known in the simplest solutions of general relativity, and this was the state of affairs after such singular solutions were pointed out. Okay, the key question was, these are fine, they are solutions of Einstein equations, but do these singularities actually form from a realistic model of collapse of a star? Okay, if you actually write down time dependent equations where a star is collapsing, just like the question was asked a moment back, if you write the equations in full generality, then do you actually get these solutions? I mean, these are solutions of differential equations, but you have to show that they arise out of a realistic collapse of a real star. And this was more or less done by Oppenheimer and Snyder in 1939, way back in 1939. So that question was partly resolved, that yes, there are models where you can do exact computations and show that really the solutions I have just indicated, like this, arise or are consistent with the collapse of realistic stars. The next question is, the singularities I just told you, the singularity here at r equal to 0, for example, is it an artifact of high symmetry of the solutions? Okay, because Oppenheimer and Snyder, when they did their computation, assumed spherical symmetry. So they assumed a spherically symmetric star, and that's how they did their computation. So natural question, and this was coming from the Russian group, and there were a lot of to and fro. And in fact, I think the earliest editions of Landau and Lifshitz classical theory of fields even contained a statement that singularities will not exist if solutions are not highly symmetric. Okay, if you don't have spherical symmetry, if there are slight perturbations which will happen in real stars, singularities will go away. So these are just artifacts of too simplified a set of solutions. And this is the reason why Penrose, when he came onto the scene in 1965, made a big contribution, because his analysis showed that it really does not matter whether the solutions have any kind of symmetry or not. If you make some very basic assumptions and use certain tools of differential topology, you can actually show that singularities are quite generic. Okay, they are not because you assume that geometry is spherically symmetric or made some assumptions on the content of the collapsing star. They are quite generic if just one or two conditions are satisfied. Okay? The big question, which we won't be able to discuss in this talk because nobody knows the answer to that, is if the singularities do survive, what is actually their structure and how do quantum effects alter the structure? That is a problem in quantum gravity, which is more or less an open problem, and we don't know what the real solution is. Okay, so we are going to discuss classical singularities. Okay, so for that, it's good to first get it straight what we mean by a space-time singularity. I already mentioned this in the beginning of the talk. It's not space-time singularity is somewhat different from singularities that you encounter in theories like electromagnetism. Okay, divergence in curvature tensor and all those stuff is really not a good handle, because they may depend on your choice of coordinates. Components of Riemann tensor are dependent on the basis in which you are trying to write those components. And because your metric has indefinite signature, it's minus, plus, 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 it's space-time you're talking about. Even the invariants may vanish, even though the space-time is singular. Okay, so there are these hiccups, and that's why it's not very straightforward to just look at something becoming infinite and call it a singularity. But more importantly, the way Einstein formulated his whole theory of general relativity, singular points are excluded from the definition of space-time itself. Space-time is supposed to be comprised by regular points. Okay, so by all logic, singular points have no right to belong to the manifold. Manifold is comprised of regular points, and the best you should be able to do is only use some pointers to point at the singularities. So singularities don't belong to the manifold, but you can say that, look, if you go in this particular direction, some singular behavior might come about. Okay, and the pointers that you use are the simplest pointers, the curves which live in the space-time. And this is what curves can do in a space-time with a singularity. So if there is a singularity which is indicated by this shaded red colored thick line there, then curves may just go and stop at the singularity because there is nothing beyond the singularity. These kind of behavior is called, or these kind of curves are called as inextensible curves. Okay, so a good operational handle on singularity is that you look at curves and you see whether if you extend a curve in a certain direction, it suddenly stops somewhere. If it suddenly stops somewhere, that is, if you cannot extend a given curve beyond a particular point in space-time, then that is a good characterization that there is something singular going on in space-time. Riemann tensor may or may not diverge at the point, but the curves are just stopping there. Okay, physically, if you are in a rocket and traveling, and suddenly your trajectory stops because further points do not belong to space-time itself, this is actually a very singular behavior. It's a definition of what a singular behavior means. So this is a good definition of singularity. Okay, and that is how we usually describe singularity in the formation of, say, a black hole. So that is the cartoon version of the Oppenheimer and Snyder collapse model that I talked about in the beginning. So at last time in the past, you imagine a collapsing shell of matter. In 3 dimension, this will be a spherical shell, for example, but in 2 plus 1 dimension, I'm denoting it by a circular patch. It collapses on this trajectory, which is marked here. At some point, it crosses the surface, which is indicated by r equal to 2 gm by c square. Remember, that is what we call as the event horizon. And then that's the point of no return. That's when you say that a black hole has formed. Once this collapsing shell enters the radius r equal to 2 gm by c square. And somewhere in the future, a singularity will form, indicated by the wiggly line there. Okay. So what I've drawn here is essentially a figure version of what Oppenheimer and Snyder did. And if you zoom into the region close to the horizon, you will see you can draw light cones, and this is where I'll use your knowledge of special relativity. You can actually draw light cones, and you will see that as soon as you cross the event horizon, look at this tilted light cone, for example, the light rays and also the time-like rays which are constrained to lie within the light cone are all bent in the same direction. Okay, just compare the light cone here. There is a time-like curve which goes to infinity. It means that as long as you're outside the event horizon, you can escape to infinity. But as long as you have crossed the event horizon, all the time-like curves are directed towards the singularity. So that is the reason why a black hole becomes a point of no return. Everything that crosses the event horizon will eventually hit the singularity. Okay, so that is eventually a summary of the picture we have of formation of a black hole and its singularity. Charles, can you roughly indicate to me how much time I have?
10-15 minutes.
Okay, yeah, that should be enough. Yeah, thanks, Charles. So let us come to the discussion of finally the key points in the proof of singularity theorems. And before we go to Penrose, I think I must mention the contribution of Amal Raychaudhuri to this, because his equation, which was derived actually in 1953, plays a key role in the characterization of singularities in space-time. Okay, there's a very interesting history associated with this paper, which I have marked here. Remember that, just notice the date of submission, the date and the date of publication. Okay, the initial paper which Raychaudhuri submitted got stuck with the referee. There were a lot of speculations and it was not accepted. Okay, he resubmitted the paper with the speculations removed and titled it a bit more modestly, and it was published after almost a couple of years since his first work was done. Okay, but Raychaudhuri equation is something which plays a key role in the singularity theorem. So let me explain what the equation tells you. And the physics of this equation is something people use even in fluid dynamics or the study of deformable media. So this is nothing exotic. The only difference in general relativity is we use this equation in space-time to characterize curves in space-time, whereas a material physicist will use it for describing a deformable medium. A fluid dynamics person will use it to describe the flow of a fluid. Okay, we will use it to describe trajectories in space-time, like I'm doing here. Okay, so imagine a set of curves, time-like trajectories on which test particles are moving, and take a cross-sectional area of this bunch of curves. Okay, so that this is the cross-sectional area I've drawn separately. It will have some shape. Okay, as you evolve the cross-sectional area, as you track this cross-sectional area along the congruence, okay, that is, you are trying to study the time development of this cross-sectional area, 3 things can happen. And this is all again going to suit your intuition very well. You can have isotropic expansion of this patch. It can just expand equally in all directions. So if it was a circle, it will become a bigger circle. That's what you mean by isotropic expansion. And you can measure it by a parameter h. You may call it the Hubble parameter or something. It just gives you the fractional rate of increase of area. Okay, so area was this before, now it becomes this. An isotropic part of the expansion is what you call a shear. Okay, so you can already see why it can be called as a shear, and it's described by an object, a matrix, which is denoted as sigma AB. And it can also twist. Just imagine that the congruences can actually twist around as they evolve in time. And the twist part is described by what is called as rotation, indicated by omega AB. Okay, if you are doing fluid dynamics, this omega AB part will be responsible for creating vortices in a fluid. Okay, that is the measure of rotation of the streamlines of a fluid. Okay, So this is essentially the three quantities which can describe how a patch of cross-sectional area of a congruence evolves with time. Okay. And the equation of Raychaudhuri actually discusses, it's actually a differential equation for expansion of the congruence. The parameter h I indicated before, the expansion, isotropic expansion. This quantity nabla u is a shorthand notation for time derivative, just a fancy notation for time derivative of h. On the right hand side is an object which is called as Ricci curvature. It is a quantity derived from the full Riemann curvature tensor. Please don't worry about it. All that we have to know here is that when you use Einstein equation, this quantity is precisely rho plus 3p by c square. Okay. I hope you are able to connect it with the previous equation I showed for the divergence of gravitational field. It was the same combination which comes even in that equation. Okay. And for the same reason as well. Okay. And the physics of the rest of the term is very obvious. If there is a shear, it will contribute negatively to the expansion. If there is rotation, it contributes with a positive sign. Okay. And this also you can understand, right? If there is a rotation, there is a centrifugal kind of effect, and the expansion will tend to increase. So h dot will have a positive contribution from rotation and a negative contribution from shear. And Raychaudhuri, if you look at his the abstract of his paper, mentions that a simple change over to anisotropy, but without introducing spin, does not solve any of the difficulties of isotropic cosmological models. In my view, this is a strong hint that he already knew that if you ignore rotation in this solution, then just the presence of sigma square will not drastically affect the expansion of these congruence, or the relation, the governing of the expansion of the congruence because of the curvature term present here, because both the curvature term and the shear term comes with the minus sign. So if you ignore rotation, the solutions may not become much different. Okay. So what really happens is, and this is really from the theory of elementary differential equations, just stare at this equation, and then you can easily see that if expansion was negative, if the congruence was converging so that the expansion is negative, areas are decreasing at some instant of time, the expansion will go to minus infinity in a finite proper time. I'm not going to give you the analysis here, but it follows just from the mathematical structure of this differential equation. As long as RAB UAUB, which is rho plus 3p by c square, is positive, this is called as a strong energy condition, by the way. If that holds, then the expansion will eventually go to minus infinity. Expansion going to minus infinity means that this patch of area will eventually collapse to a zero area. Okay, it will eventually, so that is the effect of the background gravitational field. A patch of area will eventually collapse to zero size under evaluation. Okay, and this, as we see, lies at the heart of singularity theorems, and it is at this point that Penrose comes in. And in his paper, in his landmark paper, essentially responsible for the Nobel Prize, he used the powerful tools of differential topology and what are called what has come to be known as global methods to analyze black hole singularities, use Raychaudhuri's equation to deduce some properties of congruences in presence of a black hole, and then show that if in addition to Raychaudhuri equation some global conditions are satisfied, then no matter how asymmetric the collapsing object is, a singularity will form. Okay, so I will skip this slide, but you should go to his some details about the work of Roger Penrose. Apart from singularity theorems, he has done an amazing variety of work, and I think you should go and read it up. Because of lack of time, I just skipped that slide. Okay. So in addition to Raychaudhuri's equation, the key notion which I want to describe before I end the talk, which Penrose introduced, was the idea of a closed trapped surface. Okay, so this picture is taken from Penrose paper, and it again shows the collapse of the Oppenheimer-Snyder collapse, which I also discussed before. So in the past, there is a spherical distribution of matter, but as I said, that doesn't need to be assumed. It can be aspherical, there could be asymmetries and all those things. It collapses across the event horizon, and it collapses eventually to a singularity. But inside the event horizon, you see this thick black circle, Okay, that was the key new object which Penrose realized will appear in any kind of gravitational collapse across the event horizon. And this surface, it's a two-dimensional surface which is represented there as S2. Okay, it's a sphere, a standard normal two-dimensional sphere, which is called as the closed trap surface. Okay, the property of this surface is very simple to understand. Okay, and let me indicate it here. Okay, so essential idea about closed trap surface is the following. Okay, although it's a sphere, I am indicating it as a circle here because a sphere will be more difficult to analyze on a two-dimensional sheet. So imagine a circle and imagine sending light rays at every point, from every point on the circle. So this is just your basic Maxwell's theory. The light rays which are ingoing will converge towards each other. So the blue lines there will converge towards each other, like you can see from the figure. And the outgoing light rays will diverge. Okay, so this light ray and this light ray, they'll diverge, they'll move away from each other. So that is what happens in normal life. Okay, you light a light bulb, place a lot of light bulbs on the surface of a sphere. Light rays emitted in the outward direction will diverge. Light rays emitted in the inward direction will converge. Okay, that's all we are saying. Okay, but inside a black hole, a closed trap surface is characterized by the fact that both the ingoing and the outgoing light rays converge. Okay, and you can see that from the figure. The light cones are so tilted that the ingoing light rays anyway converge. They were converging even in a flat, ordinary piece of space-time. But even the outgoing light rays are converged. And this strong converging effect is what is eventually responsible for the formation of singularities. Please remember that matter particles are constrained to move within the light cone. So if light cones themselves are tilted, they will eventually hit a singularity. Okay. So this was the key new idea which Penrose introduced. Because of lack of time, let me just tell you what the theorem is. So his theorem just uses Raychaudhuri equation in addition with the condition on Ricci curvature, RAB UAUB greater than 0. This is just rho plus 3p by c square greater than 0 if you use Einstein equations. There are also some milder conditions such that there should not be any closed time-like curves in space-time. Okay, that is a reasonable condition because you should not be able to go back in your past and then all kind of paradoxes will come into the picture. So you avoid that kind of a situation. You also demand the existence of something like a closed trap surface. And later work of Hawking and Penrose gave some alternate constructions as well. But this is what was there in Penrose's original paper. Further, there is some condition called as generosity, which I will not discuss, but it's some condition on the Riemann tensor. Again, it's satisfied in almost all reasonable space-time, so there is no problem with that condition. So if all these things are done, then Penrose's theorem says that such a space-time will have a singularity. Okay. Compare this with the analysis of the Russian group, which looked at curvature tensor, Einstein equations, carefully catalogued all possible singularities and declared that if something asymmetric is going on, the singularities will simply not form. Okay. In comparison to that, this is an argument based on what mathematicians call as topology, differential topology. It's a very powerful argument without using of the differential equations governing curvature, only some conditions. Okay. So let me end at, so this was all about singularities in black holes. Exactly the same kind of singularity appears also in the time reverse of black holes, which is the case of the universe itself. If you go back in time, you will see that trajectories of all the particles were converging, and we believe that there was an era called as a Big Bang in the beginning of the universe. And there is an era of inflation, where the expansion of the space-time was accelerating. Okay, so this is the picture we already have. And if you trace all the trajectories to the past, we believe that there is a past singularity, or in other words, there's a Big Bang singularity in the past of our universe as well. Unfortunately, inflation is the paradigm. It's a paradigm in cosmology where precisely this condition, RAB UAUB greater than 0, or equivalently the condition I wrote earlier, rho plus 3p by c square greater than 0, can be violated. And since that condition can be violated, Penrose's theorem does not apply as it is to a expanding universe with inflation in the beginning. So the question remains open whether our universe had a beginning, whether there was a singularity with the universe began. There are alternate theorems which I will not discuss. It's called as Bode-Gut-Vilenkin singularity theorem, which said that under some mild conditions, even though some assumptions of the theorems are not satisfied, singularities will still form in an inflationary universe. Okay, so I don't think I'll discuss this part. Instead, I will just conclude the talk by again highlighting the essential content. I hope that by the end of this talk, you have realized why Roger Penrose, his citation for the award is for the discovery that black hole formation is a robust prediction of general theory of relativity. If it was true that tiny perturbations could actually completely get rid of the singularity, then the picture of black hole formation would be completely different from what we use. Oppenheimer-Snyder model or even the more generalized models, you would have no guarantee that a singularity will form, but rather you might be left with a compact remnant object or something like that. Okay, it is absolutely essential to know that under generic conditions in a real universe, real gravitational collapse, singularities form, and hence black holes exist with the structure that we know of from Einstein's theory. An event horizon inside of which there is a singularity. Okay, whether all singularities are covered by event horizon is a different story, but there also Penrose has his contribution called as the cosmic censorship theorem, which says that every singularity is covered by an event horizon. There's no proof of this conjecture yet, but it's very strongly motivated by several arguments. So let me conclude the talk. So we have discussed singularities in black holes and cosmology. And I hope I have convinced you that singularity theorems indeed represent one of the landmarks in gravitational physics, maybe next only to the formulation of the theory by Einstein. It's definitely the first Nobel Prize in this area. And what remains a work in progress is the formulation of quantum version of the singularity theorems. That is, what does quantum mechanics do to space-time singularities? Okay, so that's where I'll stop, and I can take any questions from the audience now.
Okay, thank you, Dawood, for the talk. So if there are any questions, you can ask. Also, those who are watching the talk in YouTube, you can put your questions in the comment section so that I can read those questions to the speaker.
Dawood?
Mm-hmm.
Yeah, it's me, Titus.
Hi, Professor Titus.
Yeah. This theorem is in the context of Einstein's gravity, right?
Yes, but there have been generalizations to modified theories as well. But yes, the original theorem is in the context of Einstein gravity.
So it has been generalized.
Yes. So what people usually do is that in a modified theory, they will write the field equations where all the additional terms coming from the geometry part. So there will be GAB, the Einstein tensor, plus another tensor coming from higher curvature terms, for example. They all are clubbed as effective energy momentum tensor, and you just have to verify whether that satisfies the energy conditions.
Now, one more question.
Yes.
Regarding Raychaudhuri's equations.
Okay. Yeah.
Is there any analogous equation corresponding to? I don't know whether I am asking the right one. In Newtonian theory of gravity. Do you get? Let me ask it once again.
I think he's not there. He just lost connection, seems.
Okay. Maybe wait for some time.
Hello.
Yeah. Yes. Dawood, are you there? Yeah, I think Dawood is there.
I will just call him.
But he is in, right? Showing that he is in.
Hello, Dawood, can you hear? You are mute.
Dawood left hand. Yes.
His microphone is mute.
Yeah.
Yes, yeah. Can you hear me now?
Yes.
Yes.
I think something went wrong with my machine, so I am logging from my pad. Okay, I hope this is audible. So I'm sorry, I could not hear the question by Professor Titus.
Yeah. The question was, we have Raychaudhuri's equation.
Yes.
I'm just asking, I don't know whether the question is right itself.
Sure.
There is an equation corresponding to this in Newtonian gravity also. Raychaudhuri's equation.
Yes, there is. See, the equation of Raychaudhuri is effectively the equation governing deformations in any deformable media. So certainly in Newtonian gravity also there will be an equation like this. But I'm not sure what will be the analog of, see, the analog of the curvature term there would probably be the weak field limit of what RAB gives in the weak field limit. But I'm very sure because Raychaudhuri equation comes essentially from equation of geodesic deviation, and we do have a Newtonian version of that equation.
Okay.
So yes, I do understand that there will be a version of Raychaudhuri's equation in the Newtonian limit as well.
Okay, Dawood, I think I will. Oh, yeah, please.
Charles, can I ask you something?
Yeah, sure. I was going to YouTube to read some comments. Okay, anyway, you can ask first.
Do you explain, what exactly is space-time singularity? Because I don't know exactly what is singular.
Yes. So is my slide still visible?
No, I think slide is gone.
Okay, let me try to share.
It's not.
Let me. Is it visible now?
Yes.
So let me just.
Yes, it's visible.
Yeah. So I'm just trying to log in from a different machine. Yes. So effectively, what eventually right now our current understanding, and everyone agrees that that is what you should mean by singularity, is that you look at curves, time-like, space-like, or null curves, null in the sense of light-like curves in space-time. You fix one endpoint of the curve, and you extend the curve in the other endpoint of the curve as long as you can. If the curve can be extended to the values of the parameter from minus infinity to plus infinity, so let us call lambda is the parameter along the curve. If it can take all possible values from minus infinity to plus infinity, then you say that that particular geodesic curve is complete. Now, singularity is when the parameter of the curve does not take all its possible values. Suppose it goes to some finite value and stops. And you just say that this is a singular behavior because the curve has suddenly stopped. You have extended the curve as far as possible, but it still does not take all possible values of the affine parameter. And it's also sort of visible in this picture. So if you look at curves inside the event horizon here, you will see that the curves eventually go and hit the singularity. Okay. So you say that a Schwarzschild black hole, the simplest black hole in this picture, has a singularity because if you draw curves, there do exist curves in this space-time which cannot be extended to all possible values of their proper time parameter. Okay? So that is our current understanding. Earlier, people thought that a singularity should also be associated with points where the Riemann tensor diverge. Okay, but so far, as I know, there is no proof that the inextensible behavior of curve is always accompanied by divergence of curvature tensor. It may or may not happen, although it does happen for this black hole, which I have shown there.
What happens to curvature scalar at singularity?
That is also not clear, Charles, because there are, in fact, Penrose himself pointed out a very special type of space-times. These are called as plane wave space-times. These are called as plane wave space-times, in which all curvature invariants are zero, but still there are curves in the space-time which are inextensible. So you will still say that the space-time has a singularity, although all curvature invariants that you can possibly construct are just vanishing. And this can happen in a metric which has a Lorentzian signature, right? There is 1 minus and 3 plus signs in the metric. So it's not guaranteed that things like Frischmann scalar, RABCD will be positive definite.
Okay.
No, the problem was, when you talk about singularity, can you hear me? Hello?
The voice is cutting a bit. Yeah.
Yeah, when you talk about singularity, can you say something about singularity of the space-time itself, or do you really need a geodesic for that thing?
Yeah, that's actually a very good question. That's a good, and that's also a tricky question. This is what I was trying to mention here. We do interpret these things as singularities in space-time, but since singular points by all means are not supposed to be part of the manifold, because the way the theory is formulated, it's in the terms of differentiable manifolds, and these are supposed to be comprised by points which are regular points of space-time. So there is no question of people have argued about this for years, and the consensus seems to be that it does not make sense to include singular points as part of space-time. So what you do is choose curves, or time-like or null curves, which belong to the space-time. Look at the behavior of those curves and use them as pointers. So if those curves behave in a specific manner when they are heading towards a certain region of space-time, the way I have described it, they will be inextensible if you extend it to all possible points of space-time. The affine parameter will not take all possible set of values. So you use these curves as pointers, and you assume that if the curves are not extensible, there is a singularity in space-time itself. So you are using curves, you are using the properties of behavior of curves on space-time, and you are using that property to deduce that the space-time might itself have some kind of a singularity. Okay. But I understand that there is a duality in that question, whether you interpret it as singularity of a congruence or a singularity of a space-time. Okay. What I've indicated is how it is often interpreted.
Okay, thank you.
Okay, so I will just quickly read a couple of questions from the YouTube.
Sure, Charles, yeah.
So one question is about GR. So basically asking whether GR is insufficient to explain singularities.
Yes, yeah. So that is more or less going to be true, because any theory which has in itself some kind of a singularity, you expect that it is signaling the breakdown of the theory itself. This is what I've indicated in this last slide. So yes, in a sense, Einstein theory cannot handle singularity by itself, because as I was just replying, either singularities are not part of the manifold on which Einstein equations and the space metric and everything is put, or the curves which actually do belong to a manifold, when they hit the singularity, without further extra information coming, for example, from quantum theory, you cannot say anything about the structure of the singularity. And that is also one, you may call it as a weakness of Penrose's theorem, that although it tells you that singularities will always appear, it does not tell you what will the singularities look like, what is the structure of the singularity, how will you, if you hit the singularity, what kind of a surface are you hitting? Okay. Whether you are hitting a singularity as a point in space or as a point in time or as a moment in time. So none of these questions are part of Penrose's theorem. Okay. It only says that a singularity exists, and yes, you can conclude that general relativity itself is going to break down at the singularities, which is why you need a framework for quantum gravity which supersedes GR and which naturally tells you that if not a singular behavior, something else must replace space-time itself. So space-time may not be the right structure. It may not have the structure we are familiar with as given by Einstein's formulation near a singularity. The structure of space-time might itself break down, and you may require completely different structure to describe space and time. They may not even be unified near the singularity. And there are very highly speculative, imaginative ideas starting from Wheeler as to what might actually happen if GR gets superseded. There is a very fantastic idea called a space-time foam, highly speculative, which tells, this is Wheeler's idea, which says that space-time may give over to a foamy kind of structure near the singularity, and all concepts of conventional space and time will break down there. Okay? But you can keep going on and on and on. No one knows the answer. What is the correct structure you should use to describe region close to a singularity? But yes, GR is not the full story.
Okay. Another question is, I will summarize the question. It is something like, we call black holes as solutions to GR, Einstein equations.
Yeah.
But why not we call stars as solution to GR? I think
no, you do. Yeah, you do. You most certainly do. Okay. So if you want to describe stars, I think the reason might be more to do with the way these analyses were done historically, although I'm not sure. But if you look at Chandrasekhar's book on stellar structure, as I said, you can use Newtonian laws of gravity to say a lot about the equilibrium behavior and shape and structure of stars. Okay, so stellar physics was well studied even before people started using full equations of general relativity to describe stars. Okay, but black holes are objects which cannot really appear from Newtonian equations. These are firmly the predictions only of GR, and that may be the reason why people don't call stars as solutions of GR, although they are. A fully relativistic star must be described by equations of general relativity.
Okay, another one is, how does dark energy affect singularity?
That again is a very good question. Dark energy actually was introduced in some of the later works, I think by Penrose and Hawking himself, if I'm not wrong. But the only difference which the presence of dark energy can make is that it can violate one of the energy conditions. Again, everything boils down to Raychaudhuri equation along with, let me just go over to the slide. Charles, the slides are moving, right?
Yes.
So you look at this condition, rho plus 3p by p square. If there are dark energy models which can violate these conditions, okay, that is possible, right? Dark energy is as weird as things can get. So maybe the pressure is negative or rho is negative. Then one assumption of the theorem goes for a toss, and people have speculated that maybe instead of a singularity at the center of a black hole, you have what is called as a de Sitter like of core. De Sitter is a solution of Einstein equations precisely with something like dark energy. It's a solution with cosmological constant, but you can also find similar solutions with a more general model for dark energy. And people have speculated that it is possible that that solution replaces the singularity if there is something like dark energy present. The only problem is no rigorous computation supporting it. Okay. But yes, it's a good question to ask, because dark energy is often thought to have a repulsive effect on geodesics. So you can ask whether presence of dark energy can completely throw off singularity. It certainly distorts the structure of the singularity, but you have to do the full computation of gravitational collapse in presence of dark energy. Under certain conditions, the singularity may still survive. I'm not aware of any rigorous result which says that singularities are always resolved when you account for dark energy in the Einstein equations.
So any other quick questions? I can maybe take one more question. Okay, in that case, I will ask one final counterfactual history question.
Okay.
So if Hawking was alive today, would he have won a Nobel Prize along with Penrose?
I am not sure of that, Charles, because Hawking was always upset that Hawking's point was that he should have gotten Nobel Prize for Hawking radiation, which would not have happened because there are not sufficiently small black holes.
Yeah, and there is no experimental evidence.
Exactly, yeah. For singularity theorems, I think that the key ideas were all there in Penrose's work. Hawking's work extended those theorems. Many conditions were relaxed, many new conditions were added. And of course, Hawking also set up the singularity theorems for cosmology. Okay, Penrose did it for black holes, Hawking did it for cosmology. So I really don't know whether Nobel Committee would have divided the prize. Yeah.
Okay, so I think I will hand the chair to Hari Krishnan, Secretary of APT.
Yeah.
Hello, everyone. Dr. Dawood's presentation of this topic, starting from the basic principles of general relativity and moving all the way in a systematic fashion, moving all the way to Penrose theory on singularities. It has been very lucid and accessible to anyone new to this topic. I think the students as well as teachers who are attending this webinar, both in the Google Meet and as well as many of them are in the YouTube live stream presentation. So I think all of them have been enjoying this presentation, and they have got something to come back to and read more. It has been very much motivating. And on behalf of all the participants and the organizers, I thank you, Dr. Dawood, for a very lively presentation. Thank you.
Thanks. Yeah, it was a pleasure giving the talk.
Thanks to all the participants and the resource persons. I mean, the organizers. The organizers were the CUSAT Physics Department as well as Academy of Physics Teachers Kerala. So thanks to the organizers as well as the participants. Thank you all.